You've been told the F-117 is ugly. So why did the Pentagon spend a decade hiding a jet that broke every aerodynamic rule on purpose? In the next few minutes, we'll show how a faceted, unstable shape, nicknamed the Hopeless Diamond, became the only viable answer to radar networks that traditional fighters couldn't beat. By the end, you'll see why Lockheed's Have-Blue demonstrators, guided by the Echo computer tool, traded speed and agility for a radar cross-section near 0.001 square meters, and why that decision rewired how air defenses are penetrated. Before we move on, please take a moment to subscribe to the channel and like the video. You don't beat a wall of radars with tighter turns. You beat it by not showing up on their screens in the first place. Late Cold War air defense belts put search, acquisition, and fire control radars in layers, and they cued each other fast. High and fast used to buy time, and electronic jamming could blind a sector. But by this point, the margin had thinned to seconds. Batteries moved, frequency-agile sets shrugged off simple noise, and radar-guided missiles took shots from angles that classic tactics didn't expect. The design world had a habit that made sense for lift and stability: smooth curves. Those shapes eased airflow, reduced drag, and gave predictable handling. But to a radar, they behave like polished mirrors. They send a bright return back to the source across a wide set of aspects. If the threat is energy bouncing off you, a graceful fuselage becomes a beacon. So the core constraint flipped. Minimize radar cross-section, not drag. RCS is the shadow you cast on a radar. A smaller shadow means the operator sees you later and the engagement window shrinks. If you have detection range, you cut the volume a defender can search by a factor of 8, because range works in 3 dimensions, and that buys minutes for ingress and egress. In any case, the math of survival began to favor signature over speed. By way of example, the Vietnam War and the 1973 conflict showed what modern SAM belts could do with SA-2 and SA-3 systems driving losses. A Defense Science Board view in the mid-1970s concluded that a Central European fight would put strike aircraft under a dense lid, where traditional suppression would not clear enough paths. One way or another, the United States needed a strategy that didn't rely on outrunning or overpowering the network. DARPA framed that need as a testable requirement. Prove you can drive RCS down with geometry first, and use materials as a secondary aid. Lockheed's Skunk Works answered with a shape that looked wrong to pilots, but logical to an engineer modeling reflections. The faceted, hopeless diamond broke the curves on purpose so returns could be pushed off the line of sight. It was therefore a bet that controllable reflections would matter more than smooth airflow. The escalation came from the limits of 1970s computation. Modeling the electromagnetic behavior of curved surfaces across frequencies and angles wasn't something you could solve reliably with the machines of the day. Flat panels and edges, however, could be calculated, and then arranged like tiles so the strongest returns went anywhere but back to a radar. The visual analogy is a disco ball turned away from the spotlight. The light still hits, but you don't get the glare head-on. A specific tool made that practical. Lockheed engineers used the Echo, also referenced as ECH-01, to compute returns from discrete facets and edges. And they drew on edge diffraction theory to place those facets so that specular spikes and edge scattering didn't align with common threat angles. That gave designers a repeatable method rather than guesswork, and it let them treat the airframe as a map of controlled bounces. This is the mini payoff. The ugly facets weren't a styling exercise. They were a calculation that pushed energy off-axis and drove apparent signature down toward the small number regime cited for the concept. If you add internal bays and align edges so panel lines tell the same electromagnetic story, you make the aircraft harder to hold in a track long enough for a missile to guide. Having picked stealth over aerodynamic grace, the next problem arrived immediately. Make that unstable shape fly on schedule, at night, and hit aim points deep inside those radar rings without giving the network a second chance. So, having chosen to redirect radar energy instead of airflow, the next question was blunt. How do you keep a radar ghost in the air long enough to drop a bomb and leave? The answer started with Have Blue adopting flat facets, an internal bay, and strict edge alignment so panel lines and planform brakes told the same electromagnetic story. Intakes got buried with serpentine ducts to hide fan faces, and the exhaust sat high, shielded by the wing body, trading ideal breathing for a quieter signature in both radar and infrared. That geometry came with aerodynamic penalties. The lift distribution was uneven across the planform, and the body ignored smooth area ruling, so transonic drag rose while pitch and yaw stability margins went negative. Tail surfaces were sized to command authority rather than to carve turns, and they sat where the facets allowed, not where a textbook would place them. It was therefore an airframe that wanted to diverge unless a computer insisted otherwise. Propulsion followed the same logic. Engineers fit two non-afterburning derivatives of the GEF404. No reheat meant cooler plume temperatures and fewer cues for heat-seeking sensors, and it avoided the pressure spikes and acoustic signatures that come with a burner light. The exhausts used a flattened, mixed-flow layout that spread and mixed the jet with ambient air, cutting the hot core and the bright infrared streak a circular nozzle would throw. You paid in thrust efficiency and in top speed, but you got a quieter thermal footprint. The intakes sacrificed ideal pressure recovery for stealth. Screens and S-bends blocked the direct line of sight to compressor blades, which are strong radar reflectors, and that added distortion and loss that a conventional fighter would never accept. One way or another, every duct, lip, and splitter served the signature budget first and the engine's comfort second. Avionics took a similar pivot. No traditional search radar sat in the nose because antennas and emissions are liabilities when you want to be unknown. Navigation ran on a tight inertial system corrected by GPS, and mission planning pre-computed routes, altitudes, and timing to seconds. The attack sensors were thermal imaging arrays coupled to a laser rangefinder and designator, so the crew could spot a heat-contrasting aim point and hand a coded beam to a guided bomb without broadcasting their own position. Keeping it flyable required digital help from liftoff to landing. Quadruple redundant fly-by-wire watched the airframe at millisecond cadence and trimmed constantly, because the static instability would otherwise wander in pitch and yaw with every gust or bank. The result felt wobblin' in pilot slang, but it held attitude within the narrow corridor needed for a precision release, and if one channel failed, 3 remained to vote out errors and keep control laws intact. Weapons stayed inside because pylons and bombs bloom radar returns. The bay carried up to 5,000 pounds, typically a pair of laser-guided bombs like GBU-10, GBU-12, or the deep-penetrating GBU-27 and BLU-109 variants when hardened targets demanded it. Later, the jet-integrated GPS/INS guided JDAMS, which fit the same internal carriage rule and allowed releases through weather when laser energy could scatter. Combat usage proved the trade worked in practice. During Desert Storm, F-111s drew night assignments against command nodes and air defense centers in Baghdad and other dense belts. Loss rates stayed low, not because they outran missiles, but because radars struggled to form and keep a fire control track long enough to guide one. Targets that required precise aim point placement, roof vents, bunker entries, antenna farms, fell to repeatable, pre-planned ingress and clean, on-time release. So the instability was a budgeted cost, paid to buy a narrow signature and the precision to exploit it. The designation F and the program's long silence make more sense with that frame. The shape did the fighting, and keeping it out of view was part of the employment plan, which leads directly to why the name, the basing, and the sortie cycle looked more like a black project than a frontline fighter. The facets and the twitchy handling were not mistakes. They were the cost of solving radar with geometry when computation and materials limited other paths. It was therefore a purpose-built answer to energy management, not a failed fighter dressed as a bomber. If you want a follow-on covering how later designs kept low observables while adding agility and broad sensors, say so below. We can walk through the move from facets to smooth curvatures, inlet treatments, and sensor fusion. In any case, when radar energy is the problem, the correct shape may offend pilots, but it obeys physics and code, and that is why it worked when it mattered.